So we've looked at empirical formulas and how important it is giving us a ratio of the different atoms to each other so that we can use that then to find the molecular formula, that mystery molecular formula that we've been looking at for so long. So in order to find the empirical formula, remember this is a stepwise process, so first we get the percent composition, then we use percent composition to get the empirical, and then we use empirical to get molecular. So we're going to start now by figuring out how we would calculate empirical formulas from the percent compositions. And this is a multi-step process, so we'll look at the steps, and then we'll do some practice problems. So step number 1 for finding the empirical formula would be to list your givens. Right, so it's going to be a word problem. Just write down what we know. And it's usually going to be in percents. Sometimes it's going to be in grams. So let's write that down. So it's either going to be percent or grams as our givens. Step number 2 then is going to be to change your percent to grams. All right, if it's not already in grams, go ahead and change the percent to grams, and I'll show you how to do that. Once we have that, we're going to change the grams to moles. And from there, we can divide everything by the smallest number of moles. And then write your formula. So to change your percent to grams, you just do that if it's not in grams already. So if it's already in grams, you can skip step number 2. And then changing grams to moles, hey, that's just G to mole. That's something we've done a lot of. It's used in the periodic table. What we're doing then in step number 4, when we divide everything by the smallest number of moles, when we do that, that gives us our ratio. Oops, that says to get the ratio. Once we have that ratio, then we can write the formula, because the formula is just the ratio of the elements to each other. All right, so armed with those steps, let's go ahead and hop to the next slide, which is going to be a practice problem for finding our first empirical formula. This is so exciting. So we're going to calculate the empirical formula for a compound containing 40.05% sulfur and 59.95% oxygen. So a scientist in a laboratory somewhere found out these percents of the different compositions. So step number 1 was to list our givens, and our givens in this case are 40.05% sulfur and 59.95% oxygen. So 40.05% sulfur and 59.95% oxygen. So there's our percent composition. We're going to use that then to find the molecular or the empirical formula. So step number 2 is to change percent to grams if it's not given to us in grams already, and it is given to us in percent, so we need to convert that over to grams. This is the easiest step. So let's say, for example, we've got, well, let's just throw a number out there, 100 grams. We've got 100 grams of this unknown compound. So if we have 100 grams and 40.05% of this 100 grams is sulfur, then how many grams of sulfur would it have? It'd have 40.05 grams of sulfur. So if we have 100 grams, 40.05 grams of it would be sulfur, and 59.95 grams of it would be oxygen. So really, we can always just assume we've got a 100-gram sample. And if we've got a 100-gram sample, then figuring out what the grams is just as easy as erasing that percent sign and drawing in a G. So we have 40.05 grams of sulfur and 59.95 grams of oxygen. It's that easy, folks. So the next step, step number 3, convert grams to moles. This is nothing new for us. We're going to put grams on the bottom, grams of sulfur, and moles of sulfur on top. So this is where we go to our periodic table and look at the molecular mass. Hey, here's a hint. So I know up till now we've always been putting the molecular masses just to 1 decimal place, just to the tenths place. When you do empirical and molecular formulas, you want to use as many numbers as you can. The more numbers you use, the closer your answer is going to be at the end and the less guesswork you have to do. So instead of just saying 32.1 for the formula here, for the mass here, I'm going to call it what it really is, which is 32.064. And grams cancels out grams, and so that means it's 1 mole. That means we have on our hands 1.2 3.49 moles of sulfur. And for oxygen, we're going to do the same thing. So 1 mole of oxygen is, we're going to use all the numbers on the periodic table, 15.999 grams of oxygen. Grams cancels out grams. And we have 3.747 moles of oxygen. Okay, so that was step number 3, where we changed from grams to moles. Now we're going to divide everything by the smallest number of moles. And this is going to give us the ratio. So which one of these two numbers is smaller? Is it 1.249 or is it 3.747? If you said 1.249, you would be absolutely correct. That number is smaller. And since it's smaller, we're going to divide both of these by that number. So that means we're going to divide 1.249 by 1.249, and yes, that will give us 1. We're also going to divide 3.747 by 1.249, and that'll give us something else. So when we do this, when we tally this out, we find out that it's 1 for this guy and 3 for this guy. So since we've converted it to moles, we now know that the mole ratio of sulfur to oxygen is 1 to 3. So the ratio of sulfur to oxygen is 1 to 3. Since we know that ratio, that means the formula would be S1O3. So that right there would be our empirical formula. So what you do is you figure out how many moles of each there is. You set up a ratio based on those moles using the lowest number and dividing, and that gives us the ratio, and we just take those numbers and plug them into the formula. All right, let's try another one. So calculate the empirical formula for a compound containing 48.64 grams of carbon, 8.16 grams of hydrogen, and 43.20 grams of oxygen. And they were very nice to us on this one. We don't need to convert percentage into grams because it's already in grams. So let's go ahead and list our givens, which are already in grams. Okay, so there's our givens, the 48.64, 8.16, and 43.2. Now let's hop on to step number 3, which is convert grams to moles. So 1 mole of carbon, that would be 12.011 grams. Grams cancels out grams. So that means we have on our hands 4.050 moles of carbon. And for hydrogen, we're going to say there's 1.0079 grams for every 1 mole. And that means we have 8.096 moles of hydrogen. And lastly, oxygen, 15.999 grams for every 1 mole. And that means we have 2.700 moles of oxygen. So, step number 4, divide everything by the smallest number of moles. And our smallest number here would be 2.7. So we're going to divide all of these by 2.7. And when we do that, we find out that we have 1.5 carbons. We have 3 hydrogens, and we of course have 1 oxygen. So there's a problem here, and it's that 1.5. There's no such thing as a formula that has 1.5. We can't have half of an atom. We can only have whole numbers of atoms. So if we have 1.5, 3, and 1, what can we do to fix that? Now let's clear the board real quick and take a closer look at this. So 1.5 to 3 to 1 is our ratio. So if we were to write this formula, it'd be C1.5H3O. And that doesn't really work. That little 1.5 isn't going to cut it. So in order to make this look like an actual empirical formula, we need to do something to this 1.5. We needed to get it to be whole. And the way we would get it to be whole is by multiplying it by 2. Shouldn't use that color. When we multiply it by 2, that means we have 3 of those. Now, if we multiply that one by 2, what do we got to do to the hydrogen? That's right, we've got to multiply it by 2. And if we multiply hydrogen by 2, oxygen's not going to be happy until we multiply it by 2 as well. So that means there'd be 6 hydrogens and 2 oxygens. So the actual formula then would be C3H6O2. And that then gives us a nice, pretty empirical formula. That should be a 2 right there. And that shows us the ratio of carbon to hydrogen to oxygen. Next, we're going to go on and look at how we figure out empirical or molecular formulas from these empirical formulas.